It's 8:35. So let's get started. I have a couple of preliminary announcements, and they were written down here. First is a reminder to turn in your travel vouchers. Okay, you know what that means. We're going to have a group picture so we can remember this summer school forever. At 3 o'clock, right after our morning lecture, we'll all just go wherever Kendra tells us to go for our picture. I just got a picture that was taken here 2 years ago from the balcony. It's a little weird because you see the tops of everyone's head, and the top of my head is not my best side. The dinner will be tonight on the patio here. So, and lastly, there's a questionnaire going around. We ask that you fill that out and turn it in. Kendra, when do we want that by? By the end of the day or by tomorrow? Okay. Just to help us understand how we're doing with this summer school. All right. So we've had a lot of information over the last several days on specific aspects of heliophysics. Now we're going to step back and think about something common to all of them. We want to sort of unify heliophysics. And one of the unifying things, one of the things we've seen in several of the talks are shocks. In fact, the first instance of a shock was, the first one in heliophysics was the bow shock around the magnetosphere. We heard reference to that in Dr. Dorelli's talk. This is from the textbook. I think most of these come from the textbook. So this is where the solar wind hits the magnetosphere. We also have heard from Professor Bhattacharjee about magnetic reconnection, where in models of magnetic reconnection, especially according to Chapter 6 of Volume 2, we have slow magnetosonic shocks, which come out where the magnetic field lines bend. And we have a second shock, a fast magnetosonic shock, at least in solar flare reconnection, where the outflowing jets stop. So we have two shocks in solar flares. In the solar wind, when a coronal mass ejection is traveling away from the sun, we have a shock out in front of the coronal mass ejection from Volume 2, Chapter 7. As it's leaving the sun, we have a flex rope here erupting. We have a big pile of plasma that it's pushing in front of it. And, of course, we have a shock in front of that. We saw this exact figure yesterday. This is from Volume 3, Chapter 8, from Jack Gosling's talk. We have shocks in the solar wind where fast flows run into slower parts of the solar wind. And finally, we have, there we go. Finally, we have something that we heard about from Professor Justin Casper, where the solar wind actually ends in a termination shock. We also possibly have a bow shock in front of that. So we've seen a lot of shocks. The sort of summary in the textbook shows you how there are bow shocks in front of the solar wind, there are bow shocks in front of the magnetosphere, and there are bow shocks in front of CMEs. So the idea is that, here a shock is something that reappears in a lot of aspects of heliophysics. It also appears on the Earth. And here are some pretty cool pictures of shocks. I don't know if you guys have ever seen this one. A jet just about to break the sound barrier, not quite going supersonically, but as the air goes over the jet, it actually does break the sound barrier, and there's the evidence. You see this nice shock coming off of it, and a bullet being fired through the flame of a candle. There's the flame. You can see the hot air coming off of the candle, and you can see the bullet going through it, and you can see a shock out in front of the bullet. That's pretty darn cool. You can also tell from the curvature and the angles here, the bullet's barely going faster than the speed of sound. I still wouldn't want to be in front of it, but it's not going that fast compared to the speed of sound. So how many people here have studied shocks as part of some formal class, hydrodynamics, MHD. How many people have studied shocks formally? Okay. How many people have sort of taught themselves about shocks as a part of research? Yeah, that's me. Okay, so this will sort of be at a level that'll be in between both of those. If you've seen them before, this will just remind you some of the basics. If you haven't, this maybe help you build up some of your intuition. The first thing, oh man, this is really touchy. The first thing is what a shock is. We saw in several examples here, the critical thing about a shock is it's caused by a collision, okay? Just very first thing you want to know about shocks between two different gases, two different plasmas in this case, like the coronal mass ejection plasma, the ejecta, and the solar wind plasma. The other thing about a shock, my favorite definition of a shock, is it is a hydrodynamic surprise, okay? There's a collision, so there's a collidor, the ejecta, and a collidee, the thing that's collided with. That's not how your insurance, forget how your insurance company lists these people, but the party at fault and the victim. But the material, the collidee, the material that's being collided with, doesn't know what's coming. Okay, that's true of this air in front of the bullet. The bullet is traveling faster than the speed of sound. In hydrodynamics, the way the fluid knows what's happening everywhere in the fluid is essentially through pressure, which is communicated by sound waves. Okay, sound waves do in a fluid what light does in electricity and magnetism. Nothing can go faster than the speed of light in E&M. Fluids is much more exciting. You can go faster than the speed of sound. That's called breaking the sound barrier or being supersonic. But if that happens, the things in front of you don't know you're coming. And it's a surprise when you get there. Okay, so that's why it is a hydrodynamic surprise. One plasma, the collidee, is not expecting the collision. Okay, so we'll go through the details of what this really means, and we'll do that first without magnetic fields. So just plain fluid dynamics, hydrodynamic shock, so we can understand the fighter jet and the bullet and the candle, things that don't involve magnetic field or don't involve magnetic field in a significant way. We saw some of this is the equations of hydrodynamics. We saw some of these yesterday in Professor Chandran's lecture. The mass continuity equation, that is, tells us the evolution of the mass density of the fluid or the plasma. The time derivative of that being a divergence of the mass flux. The second equation, which is Newton's law. Here I've written it slightly differently. Instead of F equals ma, I've written that the time derivative of momentum is the force, or the time derivative of the momentum density is the force density, which is a divergence. Very important. It's a divergence of a flux. This is the momentum flux. It is a tensor, right? Momentum is a vector. A flux is a vector. So momentum flux is a vector of vectors. It's a tensor. We're not scared of that. We're physics graduate students. Here I've written it in dyadic notation. The pressure part is proportional to the identity tensor, and we have a viscous stress tensor. Viscosity, which wasn't part of the lecture yesterday, will turn out to be very important and in a very curious way. The way the viscous stress tensor works is it's a viscosity times a bunch of ways of writing the derivative of the velocity vector. Okay? Again, the velocity is a vector, the gradient's a vector, so we have the vi, dxj, dv, etc. The important thing here is it's a derivative of the velocity. Okay? And that is critical for shocks. We need this viscosity term. Finally, to close the system, we have an energy equation. Instead of assuming that the flow is adiabatic, as we did yesterday, it's important we don't do that. We actually have to understand how energy density is transported. And we have two types of energy density in the gas. We have kinetic energy density, that is kinetic energy of the flow, not the particles, but the fluid elements, 1/2 rho v squared, and the kinetic energy of the particles themselves in the reference frame of the flow. That's the thermal energy, pressure over, and gamma is the ratio of specific heats here. So it's 5/3 for a plasma. So this would be 3/2 pressure. Okay, so the pressure is really the energy density of the plasma, 3/2 pressure. Okay, that changes according to the divergence of the energy flux, which is a kinetic energy flux, an enthalpy flux, and some work being done by the viscosity. All right, so we have the equations. We're going to set up and solve this problem where we have one fluid colliding with another fluid. And here is the collidor. It's a big mass. Basically, it's a half space of fluid moving to the left at some velocity vi. And then we have the victim here, the collidee, the fluid that doesn't know anything's coming. That is at rest. Okay? And there's a boundary between these. That's the shock. It's not a step function. It has some change in the velocity. It's continuous. Why do I know it's continuous? What part of the equations that I've already given you tells me this can't be a step function? What? No, we can have continuity if we have a discontinuity in the derivative, because as long as the two things on the two sides are the same. There's one thing I built into this to prevent first derivatives from being infinite. The viscosity. That's critical. Without the viscosity, this could be a step function. With the viscosity is like a diffusion of momentum. So diffusions don't like step functions. Okay? So the viscosity is here to tell us what the shape of this interface is. And it's not a step function. Okay, but we have stationary fluid here, and we have moving fluid here, and some interface between them. And the interface itself is moving, and it's moving faster than this. Okay, it has to go out in front as a messenger. Okay, that's the shock. Now, the first thing we do, and this is critical, but it's the step people often forget. It changes the way things look to you. We're going to transform into a reference frame moving with the shock, called the shock frame, oddly enough. So that means we're going to subtract v sub s from all the velocities. When I subtract it from 0, I get a rightward flow of the stationary plasma. The pre-shock plasma is now moving to the right at some velocity v1. And the inflow, which was coming to the left, is now moving to the right but slower. Okay, so the way things look from the shock reference frame is very different. It doesn't look like a surprise. It looks like stuff is flowing from the left and slowing down and continuing to the right. But this is critical because it's going to help us solve these equations. So far, so good. This is the toughest part, is doing these transformations. Now we're going to make two assumptions. First of all, in this new reference frame, we're going to assume whatever the shape is, it doesn't change in time. Okay, so everything looks stationary, which is great because now we've changed from a time-dependent problem to a time-independent problem. The next thing we'll assume, and remember these assumptions because they don't always work and we'll have to come back and question them occasionally, is that everything upstream is uniform. So what you're smashing into is just a uniform material. And that's characterized by rho 1, v1, and p1. 1 is the pre-shock material. Okay, and it's just a single monolithic volume. And the post-shock material is also uniform. Okay? So after you've gone over this transition, everything is the same, rho 2, v2, and p2. Two assumptions. All right, the first assumption is great because it lets us cross out all of these time derivatives, and all of our equations are now the divergence of a flux is 0. And next what we're going to do is we're going to integrate over a volume that straddles whatever change, whatever shock we have. So one face is in this uniform downstream region. The other face is in the uniform upstream region. Another important vector, and this is critical for what we're going to do, is the shock normal. It points in the direction the shock was moving before we transformed. Now it's not moving. So it always points into the pre-shock material, into the collidor E, from the collidor to the collidee. That's the shock normal. Okay, when we perform these volume integrals, because they're volume integrals of divergences, they just turn into surface integrals. And the top and bottom surfaces are the same, so they cancel out. The front and back surfaces are different because they're in the pre-shock and post-shock, or post-shock and pre-shock material, respectively. So all we get is a difference in the flux from post-shock minus pre-shock. And I'll write that with sort of double brackets. Okay, that means jump in. So this is just basically saying the jump in the momentum flux is 0. So the momentum flux flow is continuous across this. Okay, the velocity isn't continuous, the mass isn't continuous, but the momentum flux is. The mass flux is. This is the momentum flux, also continuous. Now the momentum flux was a tensor, but we dotted into a vector, so now we have a jump in momentum. The momentum change across the shock must be 0. Both components, all the components. And finally, the energy flux. These jump conditions are known as the Rankine-Hugoniot conditions. Other people just call them the shock jump conditions. There are actually 5 of them. 1, and then this is a vector, so there's actually 3 conditions here and another condition here. The first one is pretty easy to work out. It just basically says whatever rho v is, rho v normal is, it's got to be the same on both sides of the jump condition, so it must be a constant. The other 2 conditions I can rewrite using that constant. I have rho vn times the jump in the velocity is equal to the jump in the pressure times the shock normal. That's a very important part of this. And then rho vn times the jump in this, 1/2 v squared plus, and this is basically the sound speed squared divided by gamma minus 1. That can't change. There's 2 cases that are actually going to be very different. One is if this constant is 0, okay, it could be, if the normal velocity were 0, then actually these shock conditions are going to look very different. There's no flow across the interface. In that case, we have only one constraint. There's no jump in the pressure. Okay? Right? Because that goes out and that goes out. So the pressure has to balance across it, and we have what's known as a contact discontinuity. Okay? You guys have probably seen contact discontinuities. It's an interface, a shock, some kind of boundary between fluids that are at the same pressure, but possibly different densities, possibly different temperatures. Anyone have an example from real life of where you see that? No one. Anyone here ever drunk a black and tan? Know what the heck a black and tan is? Lucas, of course. What's a black and tan? There you go. The dark beer on the top, which is actually lighter. It tastes heavier, but it's got more alcohol, so it's lighter. And then the lighter beer, so the Guinness and the Harp. Okay, the interface between them is a contact discontinuity. Don't ask the bartender for a beer with a contact discontinuity, but that's what it is. The beers are at the same pressure, at least across that interface. Oil and water, if you don't go to bars as much, is another case. Or any interface where you have cold material and hot material. Okay, it's higher temperature on the hot side, therefore lower density, same pressure. Okay, the other thing that we didn't actually have to impose, the normal velocity is 0 on both sides. The tangential velocity can be different. So we can have, well, you can't do this in your beer glass, but you can have the flow going up on one side and going down on the other. So you can have a discontinuity in density, temperature, and tangential velocity, just not pressure. That's a contact discontinuity. It's actually related to linear wave modes of the system. So if you have taken hydrodynamics, you've probably done the linear waves. So you get sound waves, but there are 5 equations. So you solve a 5x5 system, you should find 5 eigenvectors and 5 eigenvalues. 2 eigenvectors are the sound wave going this way and going that way. The other 3 are shear modes, that is velocity going perpendicular to k in both directions. Those are known as shear modes. And an entropy mode, which is a change in temperature. Both of those linear modes have 0 frequency. In the nonlinear regime, so it's not a small change in the density, it could be a significant change in the density, that's a contact discontinuity. Okay, that was just case 1. Case 2 is the interesting one. Now, whatever this constant is, it's not 0. Okay, the first thing to know now is our situation in the tangential component is just whatever this constant is, not 0, times the jump in the tangential velocity is 0. Before, we could have any jump we want because the constant was 0. Now the constant's not 0, so we cannot have a jump. The tangential velocity on one side matches the tangential velocity on the other side. Remember this. This is critical to problem 1 if your group chooses to do problem 1. If you want to see the shape of that shock around the bullet or around the Earth, as far as the solar wind is concerned, the Earth is a bullet. You need to understand this. But when we're in one dimension, and we're not a bullet, but we're just a huge mass, we can transform this away. We can move into a reference frame where we're moving at the same tangential velocity as the upstream side, and then we're moving at the same tangential velocity as the downstream side. So the flow actually hits the shock normal in this reference frame. Not necessarily the bullet's reference frame, but the new reference frame that we've gone to. Okay, in that reference frame, that's trivial. So we have a one-dimensional problem with 3 unknowns: density, normal velocity, and pressure, upstream and downstream. We have 3 continuity equations, so we should be good. 3 jump conditions, I should say. And actually, the easiest way to do this, they all have different units, is to form a ratio of the, each one of these constants, each one of these jump conditions says there must be a constant. The mass flux, the normal momentum flux, and the energy flux must be constant. I can take a ratio of those constants that has no units. That is, the momentum flux squared divided by the mass flux times the energy flux is dimensionless. It's a dimensionless constant. It's easier to work in these dimensionless situations because then I don't have to worry about the dimensions. If I do that, do a little bit of algebra, I should be able to form this dimensionless ratio into a function of the dimensionless version of pressure, density, and velocity. And there's only one dimensionless number that you can form. That is the Mach number. Okay? That is the velocity divided by the sound speed. So whatever this ratio is, it has to be a function of Mach number only. And here's that function. This is a little bit of algebra. Nothing compared to what's coming up. So I've just written it formally as f of m. So whatever the Mach number is upstream and downstream, f of m has to be the same upstream and downstream. Okay? That means formally I can write the downstream Mach number, m2, as f inverse of f of m1. So you'd think, if you understood how inverses of functions work, f inverse of f is just the identity, and m2 would equal m1, but then I don't have a change. Right? That's trivial. The important thing is f inverse is double valued. F has this shape here. Okay? So it has a minimum. So when I go to form the inverse, I have 2 branches. What I have to do is choose a different branch than I came from. So here's Mach 1. Mach 2 must be the other intersection at that same level. Does everyone follow that? I'm just doing this graphically because the algebra is a little tedious. The critical thing and the really cool thing is this function, and it's just a function of gamma, but no matter what gamma is, has a minimum at 1. Okay? So this tells us something very important that we kind of knew from the physics coming in, that when we have a shock, our upstream side has to be supersonic, has to be on one side of the minimum, the downstream flow has to be on the other side. Could go the other way, but I'll show you why I can't. So that already tells us some important things about shocks, namely that we always go from supersonic to subsonic. Here's a typical picture. So here's where I've done the algebra. It turns out you can invert that exactly. It's just solving a quadratic equation. There's the solution. This is M2 exactly written in terms of M1. You have access to these. These are the kinds of things, not these whole things I'll show you, that you'll use in problem 1. So what happens is our upstream flow is supersonic. It is higher than the sound speed upstream. It slows down. The sound speed goes up, and they switch places. So we go from supersonic to subsonic every single time in a shock. That's what happens. Because rho times v has to be constant, if the velocity goes down, the mass density goes up. Okay? The other thing that goes up is the pressure goes up. 2 reasons the pressure goes up. First of all, I've compressed the fluid by slowing down. You compress for the same reason the traffic gets thicker when everyone puts on their brakes. Right? When you come to an accident and everyone has to slow down, the density of cars goes up. Right? But also the pressure goes up. And that is actually not like an accident on a road. It's the pressure gradient that slows down the flow. The higher pressure upstream slows down the flow, makes it go subsonic. Then you can form the entropy as just the logarithm of pressure over rho to the gamma. So the difference in entropy is the logarithm of the pressure ratio minus gamma times the logarithm of the density ratio. And this is what happens to the entropy. The entropy goes up. Okay? If I tried to solve this problem the other way and go from subsonic to supersonic, what would I have violated? All of thermodynamics or just one law? Second law of thermodynamics. Okay? So that is why you have to go from subsonic to supersonic. That is why you have to increase your density going across the shock. Okay? Because, and these are the hypersonic limits. You can take the limit as the upstream Mach number goes to infinity. You'd think that that's going very fast. Actually, it's very cold, say. Okay, that's what would happen, say, if you just had a flow of, say, shotgun pellets, right? They're all going at about the same speed. So in their own reference frame, they're at rest. They have 0 sound speed. Okay, that's a Mach number infinity flow. The downstream Mach number is not infinity. It is 1 over square root of 5. The downstream density is only 4 times the upstream density. That is the limit. You cannot increase the density of a plasma by more than 4. That is the limit. Thou shalt not increase density by more than 4. Okay, and the pressure, however, upstream pressure can be as large as the upstream Mach number. But what you find out is the upstream pressure is a multiple of 1/2 rho v squared. In engineering, we call that the ram pressure. So essentially, you convert the ram pressure to thermodynamic pressure or plasma pressure. That's a shock. Now, let's get back to the entropy and the viscosity. The funny thing about the viscosity is I insisted on including it, but it doesn't appear in any of the jump conditions. So why the heck did I make such a big deal of it? Well, if I had not, if in the original derivation I had left this out, then we would be back to what Professor Chandran showed us yesterday. We would have adiabatic flow. Okay, that would mean P over rho to the gamma was constant. That would mean the upstream entropy was equal to the downstream entropy, and we know that that can't happen in a shock. Okay? So, what goes wrong? Right? I could have solved all the same equations. I'm not saying that physics could allow this, but what would go wrong if I tried to solve the same set of equations that Professor Chandran gave us yesterday and do the same steps here? Right? I would end up with the same conservation laws, and it would give me the same jump conditions, so presumably I get the same downstream flow, but it violates one of the equations. We made 2 assumptions. One of those must not be right, it must not be satisfied. Which one? Do you believe that you get the same jump conditions if you take sigma to 0? If you say set sigma to 0. Because it's just conservation of mass, conservation of momentum, conservation of energy. If you set sigma to 0, you get a fourth one, conservation of entropy. So you have 4 equations on 3 unknowns. So who would bet that we could solve those 4 equations for 3 unknowns? No one willing to take that bet? Who tells me, other than just, I don't want to go there, what would go wrong? Why we couldn't do it? We can. I mean, in the equations we can. So we can't find a solution. What has prevented us from finding a solution? We made 2 assumptions. Do you remember the 2 assumptions? So basically, one of those 2 assumptions must be invalid in this case. What? Stationary. So what will happen is we'll get flow where the downstream properties just don't settle down. We'll get all sorts of turbulence or random motion or complicated motion, but not stationary motion. Viscosity is critical for damping away those motions, so we need it in the process. And the other thing is, if I use it in my problem, it disappears. Now I can take it to 0, and I will get the same answer no matter what. So the limit, viscosity goes to 0, is different than taking the viscosity to be 0. It's kind of funky, but this happens. The reason there is that the product in the formal solution of mu times dv dx, this is just the one velocity component. This is the stress tensor. This is the viscous stress tensor, one component of it. That has a constant value in the shock. So if I take mu to 0, then dv dx must go to infinity, and the product must be that constant. What that means is the shock becomes infinitely thin. The shock thickness, therefore, must go as 1 over the viscosity. So if I take it to 0, I get a step function now. OK, so that's all the sort of formal side of hydrodynamic shocks. Let's look at a couple of cases where that really happens. Here is our bow shock. So here we have an upstream flow that is going to be surprised by the Earth. Here, this is a classic paper. Professor Dorelli used it many times. It was done with the upstream Mach number being 8. Okay, so the flow is coming in at Mach 8. As Professor Casper showed us yesterday, the solar wind actually prefers to be at Mach 10, but very high Mach number. It's supersonic, much faster than the speed of sound. Therefore, it has to shock when it gets to the Earth because it needs to flow around the Earth, and therefore it needs to be subsonic. Okay? So we get a Mach 8 shock right there. And so the density goes up by a factor of 3.82. Mach 10, it will be closer to 4. Mach 1 million, it will be almost exactly 4. It will never be higher than 4. Of course, here, it goes up a little bit farther. This is basically the gist of problem 1. The flow further slows down because it can only decrease by a quarter the speed. Right? It can only go down by a factor of 4. So if it's coming in at 400 kilometers per second, after the shock, it's going 100 kilometers per second. Okay? Why is that not Mach 2? Why have I not got, if I only decrease from 400 to 100, going Mach 8 before, I go 4 times slower, how come I'm not going Mach 2? What? The sound speed is increased. When I crossed that shock, my temperature went up. So the sound speed is now much higher. That's what you'll work out in the problem. So I'm actually going almost Mach 1 over root 5. Okay, almost exactly Mach 0.4 over here. Now, that's the case that we analyzed here, a normal flow. Over here, we're actually coming at the shock at an angle. Now, in the derivation, we said, well, let's just shift to a reference frame where we're going normal. But here we want to stay in the Earth's reference frame. So what we have to do is consider this component of the flow is the Mach number. It's actually 8 times whatever cosine of 49 degrees. So it's Mach 5.2. And the jump in density is a bit lower, sorry. So we'll get to a jump of only 3.6 over there. Okay, see how that works? The other thing is, though, the tangential velocity is continuous across this. So what you actually end up doing is the flow bends. The flow speed normal slows down. The flow speed tangential doesn't, so you bend that way. Finally, if you carry out this argument in your head, far, far away, where they haven't solved these equations, you'll have an angle where the inflow, normal to the shock, is Mach 1. That's the slowest you can actually get a shock at. And if you work that out, the angle that shock must be making is the arc sine of 1 over the Mach number. That's known as the Mach angle. This is known as the Mach cone. This is if you ever see a sort of simple physics derivation of the sonic booms, this is what they show you. This is the asymptotic shock wave that comes out of there. It's a very weak shock. The jumps are very small, but it goes out at that angle. Here is the situation in the interstellar medium. We have flow. Again, we're in the reference frame of the Earth, which is in the solar system. So in our reference frame, we see the galaxy's material coming at us going 25 kilometers per second. Actually, it's the solar system that's moving 25 kilometers per second through the galaxy, but we don't think that way. So we have flow coming in at 25 kilometers per second. We also have a sun here that's spitting stuff out at, number for the sounds, the solar wind speed? 2 lectures on it yesterday. 400 kilometers per second, say. So it's going 400 kilometers per second outward and 25 kilometers per second inward, so there's a collision. Actually, there's 2 collisions. We have a termination shock here. We have a termination shock here, the bow shock, and we have between them a contact discontinuity, the other thing we learned about. So this contact discontinuity is called the heliopause, this contact discontinuity. That is where the material from the sun meets the material from the galaxy. That is what people call the edge of the solar system. Everything inside the heliopause is ours. Everything outside the heliopause is theirs, meaning the nighttime astronomy community. Right? We own everything in here. It's very small, but it's ours. Everything in here, sorry. So across the contact discontinuity, the pressure does not change, but the density does. Our density is much higher because the sun produces much more stuff than the galaxy does. So we have a density jump. We have shock normals that, this is confusing. We'll get back to this in a second. This shock normal is pointing inward because the pre-shock material is the solar wind. Okay? This shock normal is pointing outward. The shocks aren't moving, but the flow is moving through them. Okay? And this is the interstellar medium coming in at 25 kilometers per second, shocking. And then this is the solar wind coming in at 400 kilometers per second and shocking. And this is the interface between them. Okay? So bow shock, heliopause, termination shock. So Voyager has only crossed the termination shock. It has yet to cross the heliopause. Okay. This is a little trick. This is equally tricky. We also saw this yesterday, I think in Professor Casper's lecture. This is the solar wind going here in this old paper by Hundhausen, 300 kilometers per second. But then there's a portion of the coronal hole that spits out something at 400 kilometers per second, so a fast stream. And here is the velocity as a function of time and a function of distance at different times. Here's that fast stream, 450 kilometers per second. And then as it goes away, it gets free of the gravity. It sort of speeds up to 500 kilometers per second and moves out. We have a pulse, and it develops into 2 shocks. So here is the pressure. The pressure jumps here, and the pressure jumps here. These are 2 shocks. You can see the shocks moving. This is what's called the forward shock because it's in front, and it is moving out away from the sun. This is the back shock, the reverse shock. It is moving out away from the sun. My question to you, which directions do the shock normals point? Away from the sun, towards the sun, or in different directions? Okay. We talked about the shock normal. We talked about it in terms of flows, about the motion of the shock. Here's a trick. It took me a long time to learn. Don't think about the velocities. If you're very good at doing transformations from one reference frame to another, you can do it. I'm not, especially not at 9 in the morning. So what should we think about instead of the velocities to tell us which way the shock normals go? Density. Okay, so I didn't plot density here, but pressure. Let's use pressure. Okay. So which way should the shock normal point relative to from which side to which side? What? opposite to the gradient, so from high to low pressure, right? So the shock normal always points from high density to low density and always from high pressure to low pressure. So the shock normals here are as such. The forward shock actually has a shock normal that points away from the sun. The reverse shock is propagating back towards the sun in the reference frame of the wind. But it's not propagating as fast as the wind is propagating. So it appears to be moving away from the sun, even though it has a shock normal directed towards the sun. Does that make sense? You can tell the shock normals just from the jumps in pressure. Okay, so this is the way these shocks form in the solar wind. We get a forward shock and a reverse shock. Okay, so those were all cases where we didn't pay attention to the magnetic field. Let's see how we're doing on time here. Good, we're exactly halfway done, and we're going to do the much harder problem, magnetohydrodynamics. Well, actually, all we do is add a couple more equations. We add a magnetic field, so we have what we saw yesterday. This is the magnetic tension force. It's actually also written as a dyadic tensor, part of the Maxwell stress tensor. The magnetic pressure, just added to the pressure tensor. We have three kinds of energy: kinetic energy, thermal energy, magnetic energy. Okay, the sum of those three has a flux, the energy flux. We have the kinetic energy flux, we have the enthalpy flux, we have this. Anyone know what that is? One of the three coolest names in physics. What? No, the Lorentz force is up here because it's a force. This is a flux of energy. So actually what its name is has the word flux in it. It's the Poynting flux, which oddly enough is named after a guy named Poynting, but it points in the direction of the electromagnetic energy flow. It's actually E cross B, and in MHD, E is V cross B. So this is E cross B. This is the Poynting flux, the flow of energy due to the magnetic field. And they have the same viscous term here. We have the induction equation. I made it an ideal induction equation. It's critical we have viscosity. It's not important to have resistivity. We can have it or not. Make our life a little simpler, we'll leave it out. And finally, we have div B is equal to 0. All right. Different equations, same strategy. We're going to assume we're going to go into a reference frame co-moving with this. There'll be two transformations, so let's keep track of them. The first transformation, I go into the shock reference frame, so this is stationary. I have flow. Now I haven't done the second transformation, so this flow could be at an angle. We have magnetic field. It could also be at an angle. Flow at an angle, magnetic field at an angle. The same assumptions apply. This will be a stationary solution in this reference frame. Everything upstream, and everything downstream will be uniform. So I just have a vector B1 and a vector V1, B1 and V1. I apologize for people to whom V and B sound very similar. This is what we've got. And they might make angles with respect to each other. Oh, man, this is tricky. Then we're going to integrate these. We're going to assume they're stationary. So all these time derivatives are 0. We're going to integrate it over a volume. So these divergences will integrate to surface fluxes, and we'll just get jump conditions. So let's look at 3 of the jump conditions here. The first 2, actually. The jump condition from div rho v is that, again, rho v normal has to be constant. This is the mass flux across the shock. The other thing is that the magnetic field normal has to be constant across the shock. That comes from div b is equal to 0. Should have a lot of respect for that. That's not one we want to violate. And then we have the momentum flux equation. So we have 2 constants, and the other equations are going to involve those constants multiplying jumps. So here's the mass flux multiplying the jump in velocity. Here's the normal magnetic field multiplying the jump in magnetic field. So what we're going to do is we're going to get 3 cases here. Case 1 is if the mass flux is 0. That led to our contact discontinuity before. Case 2 is if the normal magnetic field is 0. They're constants. That constant might be 0. Okay? Now, if we look at case 1, we have Bn times the jump in magnetic field transverse, but of course the normal component doesn't have a jump. So this is really Bn times the jump in the magnetic field vector. That must be 0, okay, in case 1. Well, unfortunately, that brings up two subcases, case 1a and case 1b. Case 1a is when I solve this equation by setting B normal equal to 0. That's also case 2, but this is case 1a. Okay? Case 1b is when the magnetic field doesn't change. These have two different names. Well, sorry, this has one name. This is the contact discontinuity. This is called the tangential discontinuity. Sorry, there's not a huge amount of jargon, but this is what we've got. Okay, so we've got two possibilities here. The tangential discontinuity, both the mass flux and the normal magnetic field vanish at the shock. Case 1b, the contact discontinuity, the normal component is not 0, and the magnetic field is constant. If we look at the tangential discontinuity and you track through it, and I'm not going to go through in great detail, but what it amounts to is there's no normal component to the magnetic field across the shock, but the tangential magnetic field is unconstrained. It can change in any way it wants. And the velocity can change in any way it wants. Okay? The only restriction here is that if we just look at the normal component of this jump, pressure plus b squared over 8 pi, so plasma pressure plus magnetic pressure can't jump. It's the only constraint on this. So because the tangential magnetic field changes, I actually have current in this layer. It's a current sheet. This is a current sheet. A tangential discontinuity is a fancy name for a current sheet. On the two sides of it, I have possibly different pressure, possibly different magnetic field, but the sum of those two is balanced. So the Lorentz force at this contact discontinuity, tangential discontinuity, is balanced by a pressure gradient. That's another way of thinking about it. Okay? So, yes. And it's possible for there to be shear across this. So there can be have a velocity, a velocity change. Now, case 1b is a contact discontinuity. Now we have a normal magnetic field going across this, but we don't have a change in the magnetic field direction. So we have uniform magnetic field, and if we track down, we basically have grad p is equal to this is equal, sorry, jump in pressure is equal to 0, jump in tangential magnetic velocity is 0. So actually, that tells me the velocity itself is 0, because there's no normal velocity, and the tangential velocity can't jump. So this is a contact discontinuity. Again, it relates to hot stuff and cold stuff in contact with each other. There's a magnetic field connecting them, but that's okay. They're still in contact with one another. And it is, again, related to linear zero-frequency modes. However, does anyone who studied MHD remember the different waves we get? We actually have 7 now instead of 5. So we have shear Alfvén waves, we have fast magnetosonic waves, we have slow magnetosonic waves, we have entropy waves. We do not have shear waves. They became Alfvén waves. So those are gone. So the only thing this is related to is the entropy mode. Okay? That's the contact discontinuity. Finally, if, case 2, B normal is equal to 0, but V normal is not, it turns out you can sort of transform away the tangential velocity, and what you get are equations that look almost identical to the ones we solved in hydrodynamics, except what you really have is two kinds of pressure. You have plasma pressure and you have magnetic pressure. The plasma behaves like a gas with gamma of 5/3. The magnetic field behaves like a gas with gamma of 2. It's just like you had two different gases and you shocked them. So not very interesting. It's just a subset of larger kinds of shocks we'll look at. So let me just then put this in context. We have sort of a grid here. We have B normal is equal to 0 or not 0. V normal is equal to 0 or not 0. This element in the matrix here is the tangential discontinuity. This is the contact discontinuity. This is the perpendicular shock. This is where we're going. Example of tangential discontinuity. This is the bow shock. We've already looked at that. Here we have what's called the magnetopause. This is where the solar wind touches up against the magnetosphere. It is not a contact discontinuity because there's no normal component to the magnetic field, at least in this simplified picture. Of course, this is very simplified. It is a tangential discontinuity. So we have to have balance of total pressure. That is the plasma pressure on one side, and it's mostly plasma pressure in this simplified picture. And over here, it's mostly magnetic pressure. That's really, I think that was one of your earlier homework problems. You can work out where this magnetopause is using the properties of tangential discontinuity. The other tangential discontinuity we've heard about is the heliospheric current sheet. There we have the magnetic field coming out of the North Pole, at least in this cycle, and into the South Pole. Between them, there's a current sheet. Remember, a current sheet's just a familiar term for a tangential discontinuity. So those are the two tangential discontinuities. And I'm lucky today, Phil Judge is not here. He'd crucify me for saying this. But in a very simplified view of the transition region, the jump from the corona, sorry, I tipped this over, so the corona's up here, temperature of 1,000,000 degrees. The chromosphere is down here, temperature of 10,000 degrees. We have an interface between hot and cold. The magnetic field goes through that interface. Here's a picture from Gabriel, 1976. One of the most reproduced figures you'll ever see in solar physics. We can see that between the cold chromosphere and the hot corona, the magnetic field goes through that interface. The normal component does not vanish. Bn does not equal to 0. So the transition region, at least in this simple picture, is a contact discontinuity. We heard a lot about IRIS. IRIS is supposed to help us understand how complicated this is. It's not a simple static situation, and that's going to be great. The one thing I hope they did not promise NASA when they promised to launch, when they got the money to launch IRIS, is that they would never see this cartoon again. My prediction, this figure will outlive IRIS. Whether we prove it's wrong or not, it's such a beautiful figure. So anyway, this is the simple picture of the transition region, and it's a contact discontinuity. The other case, which is none of those, is a general MHD shock. The perpendicular shock is just a special case of those. Let's do that now. Okay. The only thing that I really want to draw your attention to is, unlike the regular shock, the hydrodynamic shock, we cannot transform to a reference frame where V is perfectly normal to the shock, because this is what we would have used to do it. And if Bn is not 0, it is in hydrodynamics, then I can't assume the tangential velocity is the same on both sides. So which reference frame should I choose? It turns out I can choose one that's known as the de Hoffmann-Teller reference frame. Okay, I'm not going to get rid of either velocity vector or the tangential component of it, but what I do is I transform it into, if you perform the algebra here, you'll find out that this makes V1 and B1 parallel to one another. Okay, if I just perform this simple transformation, I can make them parallel. If they're parallel, the electric field on the upstream side is equal to 0. Then I can use this equation here and say, well, if it's 0 on the upstream side, it better be 0 on the downstream side, which then tells me that V2 is parallel to B2. So I can't get rid of the tangential velocity, but what I can do is line up the velocity vectors and the magnetic field vectors. That's the de Hoffmann-Teller reference frame. That's the way people think about MHD shocks. They go into this reference frame. Then the important thing is the Poynting flux in this reference frame disappears. So we have a vast simplification to the energy equation. We don't have to worry about this anymore. We've already used it. And we have much simpler jump conditions. In fact, even more than that, we now have a couple of dimensionless parameters we can work with. One is the Mach number. Actually, it's the Alfvén Mach number. It is in the de Hoffmann-Teller reference frame, it is the flow velocity divided by the Alfvén speed. Okay, that's only in the de Hoffmann-Teller reference frame, because otherwise V would be different, B wouldn't. But you can also say, no matter what reference frame you are in, it is the normal component of the flow speed divided by the normal component of the Alfvén velocity. Okay, it's V1 normal over B1 normal. So that is the Mach number that will play the same role as the Mach number in the hydrodynamic shock. But we have two other non-dimensional numbers. One is the angle. Fortunately, in the de Hoffmann-Teller reference frame, you don't have to ask me which angle, magnetic field or velocity. They're the same angle. Okay, so we just have theta 1. And on the downstream side, we have theta 2. That is the angle of the downstream flow. Okay, so we have thetas, and we also have betas. That is the plasma pressure divided by the magnetic field pressure. Okay, so 3 non-dimensional numbers and 3 non-dimensional numbers over here. Fortunately, we have 3 jump conditions. 1, 2, 3. So we should be able to succeed. We should be able to find Mach number 2, theta 2, and phi and beta 2 as functions of the others. It is a bit of algebra. I'm not going to take you through it. I'm going to draw your attention, though, to the first of these. If I use these non-dimensional numbers in this equation, okay, just the tangential part of this equation, I actually find out I have a jump condition that tells me Mach number squared minus 1 times the tangent of the angle has to be conserved. This will be important. But you could also formally, in doing the algebra, use this equation to solve for theta 2 in terms of theta 1, Mach number 1, Mach number 2. Okay? So you've all been through a lot of algebra in your careers. You understand how you eliminate variables and then move on, and the algebra gets progressively worse. Well, you do that, and this is what you get. You get a 6th order polynomial. It's actually a cubic in M2 squared. Okay? And this is the relationship. The Mach number 1 and Mach number 2 must satisfy this one condition. This is all 3 of those jump conditions lumped into one. I'm sure you're all good enough to use whatever software, Mathematica. You can plot M2 as a function of M1. This is just solving that equation. So this dashed curve here solves that equation. Now, one thing I didn't show you was, in this case, it's very simple. The ratio of Mach numbers squared is equal to the density ratio. Okay? So, and one thing I will not show you either, but you can trust me on this, the same situation occurs with the second law of thermodynamics. If I want to satisfy the second law of thermodynamics, rho 2 must be bigger than rho 1. Okay? I must compress the plasma. Only that way can I drive the pressure up, can I drive the entropy up. If I go the other way, second law is going to get me. So actually on this curve, everything above the diagonal is verboten. We cannot go there because it violates the second law of thermodynamics. So of this curve, I'm only allowed to live on the red, blue, magenta, or green portions. Okay? Now, where those intersect the diagonal, Mach number 1 is equal to Mach number 2. If I think about the very neighborhood of that diagonal, Mach number 1 is almost the same. It differs by a small perturbation from Mach number 2 and Mach number 1 differ. So density 1 and density 2 differ by a small perturbation. Velocity 1, velocity 2, you get the idea. It's a linear perturbation. It's a wave. Okay. And how many waves do we know about in MHD? 3. The number you shall count to shall be 3. You will not count to 2 unless immediately proceeding to 3. So we have 3 waves. We have the fast wave, the slow, the Alfvén wave, shear Alfvén wave, and the slow wave, 3 intersections of this curve. And that's always the case. Okay? So already it's starting to make sense. This is the 3 places that my curve intersects the diagonal. And it turns out that on each branch, here, this portion of the branch, Mach number 1 is above the slow magnetosonic wave. Mach number 2 is actually, and you can't tell it from this diagram, below the slow magnetosonic sound speed. The Alfvén wave here, same thing. This is the shear Alfvén wave, the shear Alfvén speed. That's the shear Alfvén speed. Okay, so I've just graphed this out. Now, I want to show you there are 3 regimes we typically break this curve into. There's this regime here. After it intersects the fast magnetosonic diagonal, we have this portion, the green portion. This is known as the fast shock. Along this curve, Mach number 1 is always greater than Mach number 2, both of them are always greater than 1. Okay, that's the fast magnetosonic curve. The intermediate curve, here's Mach 1, here's Mach 1. Intermediate curve, Mach M2 is below 1, but M1 is above 1. And the slow magnetosonic curve, from this diamond to the left, both of them are below 1. Okay, so this is why we break things up. This is how we break things up. Why do we break things up this way? Well, I'm going back to this equation here. If I rewrite this equation here, it tells me that the ratio of this, Mach number squared minus 1, Mach number squared minus 1, is the inverse ratio of the tangents, which, if I go back to how these are defined, and the fact that the normal component is the same, is the ratio of the magnetic tangent magnetic field vectors. So it tells me that my shocks have very different characters. In the fast shock, because these are both bigger than 1, and this is bigger than that, tangent of theta 2, and therefore theta 2 is bigger than theta 1. So as the flow goes across a fast magnetosonic shock, the angle increases. The angle of the magnetic field increases. The magnetic field strength increases. Okay, B2 is bigger than B1 in a fast shock. In a slow shock, they're still ordered the same way, but they're both below 1. So this is actually a negative number, and this is a larger negative number. So that means theta 2 is less than theta 1. So in a slow magnetosonic shock, as I go across it, the magnetic field strength decreases, and the magnetic field angle points closer to the normal. Okay? But they're both of the same sign. Okay? This ratio is always positive in those two cases. In this case, what's known as the intermediate shock, the ratio is negative. So the magnetic field changes directions. It bends across. Okay? So that's why we break the shocks up in this way. I can't tell you whether this is larger or smaller. So here's a scan of essentially changing the same upstream magnetic field direction, and if I change, and how it works here. I'm in the fast magnetosonic regime, fast shock. The magnetic field is bent away from the shock normal. As I move down this curve, it gets closer and closer to theta 1. When they line up, I have no change in the magnetic field direction, or right before that, I have a very small change. That's a linear wave. This is a fast magnetosonic wave. Okay, that's this point here. So I go down the curve. That's when the two are lined up. I magically jump over to here because now I'm in a slow magnetosonic wave. A slow magnetosonic wave is one where the pressure and the magnetic field pressure are out of phase. Okay? And then, as I continue moving the magnetic field direction down, I move along the slow shock branch. I get to this shock here, which is theta 2 is equal to 0. That's known as a switch-off shock. You haven't switched the magnetic field off entirely because the normal component has to be continuous, but I switched off all of it that I can. Okay? And then I go into the regime where the magnetic field direction has changed. The magnetic field has changed directions across the shock. That's the intermediate shock regime. And then I finally reach this point here, which is related to the shear Alfvén wave. At this point, theta 2 is minus theta 1. The magnetic field strength is the same on both sides, but the field direction is reversed. That's known as a rotational discontinuity. So there's 6 different things you'll hear about in shocks. It gets a little confusing, but they're all just related to changing the magnetic field direction. Okay, is that lining up? So that's really all there is to magnetosonic shocks. It's just where you are on this curve tells you how the Mach numbers are related to one another. Just to show you, yeah. Yes. Yes, this is the most interesting, shall I say, portion of this diagram. Yeah. So sorry, I've totally glossed over some very interesting aspects of this point here. This is not a small perturbation to the magnetic field, so this is not really a shear Alfvén wave. But if we went back and looked at some of the equations, it turns out Well, I'll point you to where I bamboozled you. In this jump condition here, if ma squared is 1, now it turns out now I really don't even have the situation that I led you all to believe, that everything was two-dimensional. This is called coplanarity. Those groups who choose to solve problem 3 will sort of see coplanarity at work. When you're working with spacecraft, you see it, and you'll see it here. Coplanarity doesn't apply there, so things are much more interesting. Ben, can we talk about it? I'm sure you don't need to, you could tell me stuff about that. But anyway, let me jump over, just make one point here. This nasty equation, again, if I take Mach 1 to infinity, I go to the hypersonic limit, there's something interesting to remark on here. I get to a very simple equation, and in fact, what I find out is the density ratio and the tangential magnetic field ratio approaches the same limit as the hydrodynamic case, 4. Okay, having a magnetic field does not help me increase the density any. And that points to a very important difference between magnetic pressure and plasma pressure. Right? When I have a way of converting kinetic energy to heat in accordance with the second law of thermodynamics, I can dissipate kinetic energy and turn it into plasma pressure, thermal energy, plasma pressure. I can't turn it into magnetic fields. That's not the way dynamos work. So in fact, the magnetic field density, the magnetic field ratio can only increase by 4. The magnetic pressure can only increase by 16. The plasma pressure can increase as much as I want because dissipation can turn any amount of thermal of bulk motion into plasma pressure. Okay, interesting thing to think about. Okay, so let's get back to some reality here. Good, we've got a few minutes. We can finish this. So here is the nice cartoon we thought about. We thought about these forward shocks and reverse shocks. The way we've learned about these, in keeping with the exploration theme of this school, is from a spacecraft like this, Voyager 1. This was Voyager 1 on its way out to the termination shock and beyond. Early on in 1977, probably none of the students, you were very, very young at that time. Here it is taking data. And this, I don't do this for a living. These things just make my eyes glaze over. But this is the way you display the data. It's measuring the proton density. It's measuring the velocity. And here it is resolved into 3 components, R, T, and N. There's the coordinate system I finally figured out. And here's the magnitude of the velocity. And the magnetic fields in the 3 directions, R, T, and N. And here's the magnitude of the magnetic field. Here is time in hours from whatever, November 27th, 1977. Anyway, here's time going forward. The spacecraft is moving out. It's going to get out of the solar system, so maybe at this time it's not really going at escape velocity, but there's it's going somewhere close or below that, 34 kilometers per second. The solar wind speed, as we saw, is 300 and something kilometers per second. In fact, relative to the spacecraft, it's 321, 282. So the spacecraft's almost sitting still. The solar wind is blowing past it. First important simplification. The other thing we see is over time, the density jumps up. So what has happened? We have crossed a shock, or a shock has crossed us. And we used to be in the upstream section, and we've crossed into the downstream section. So we have a shock normal that's pointing this way. The shock has gone over us. And you can see the density jumped by less than 4. That's roughly 2. Right? So that tells us the density jump. The other thing that we can see is the magnetic field has gotten stronger. So what kind of shock do we just cross? The magnetic field got stronger as I went from upstream to downstream. Fast magnetosonic shock. Of course, it says up here, this is a fast shock. It's a forward shock, because it's the shock going out that way. It's not the reverse shock. You can use all of these things to derive all the other shock parameters. For instance, you can figure out then which way the shock normal is. And this is a case of theta 1 is 84 degrees. And beta 1, we didn't even measure the plasma pressure here. But you know it's a fast shock, so you can figure out that beta was 15. Okay, and it got smaller as you went across. So if you choose to do problem 3, you'll work through a very simple example with a calculator, that's all it takes, and derive from idealized observations at one time and a later time properties of the shock. It turns out just from this data you can work out what kind of shock you've gotten, what the normal is. And here it was done for that. Here is another spacecraft, IC-1, crossing the bow shock, okay, going from low density to high density. So it's a shock where we've crossed from upstream to downstream over time. And you can also work out that the total magnetic field strength has increased. Again, it's a fast shock. So I showed you before the early 1960 version of the bow shock, and it was a hydrodynamic shock. Actually, it is a fast magnetosonic shock. But beta is fairly high, so the magnetic field doesn't play a huge role in understanding it. Here is a version of a sort of reversal in flow streams. This is from a paper by Jack Gosling. It's taken from Ulysses. This is a spacecraft that went out of the ecliptic and viewed the sun from the South Pole first and then the North Pole. On its way at 3.5 AU, or maybe at some other time, this thing passed it, and it's interpreted here. The density jumps up, the density goes down, the density jumps down again. So this is crossing from upstream to downstream, and then from downstream to upstream. It looks like a forward shock and then a reverse shock. Actually, if you look at the gas pressure, at least here, the gas pressure has jumped. What's not as obvious is the magnetic pressure has also jumped there. You can sort of see it there. So this is actually a tangential discontinuity. What we think is happening here, what Jack Gosling thinks is happening here, is this is a flux rope, a magnetic cloud. The tangential discontinuity is the boundary between where the magnetic flux rope is and where the other stuff is. Okay? He also claims there's a second tangential discontinuity here. Jack Gosling knows his stuff, so I'm going to believe him. I must say I can't really see it. Anyway, so we've got 2 fast magnetosonic shocks and 2 tangential discontinuities. Solar physics. We can actually see shocks at the sun, right outside of the sun. It's a little complicated. We see them in, well, we can see them in a coronagraph. This is an artificial eclipse where we've blocked out the sunlight. This is made from the stereo spacecraft, the coronagraph 1 and coronagraph 2. That's the green and then the orange. And you see a coronal mass ejection leaving the sun here. What they want you to draw your attention to is this portion here, which is in front of that, is the shock. And it is deflecting. There's a change in velocity as you go across it. But a far more interesting way of seeing this is it's a fast magnetosonic shock. It turns out it has an effect on the electrons that produces radio waves. And it produces radio waves at the plasma frequency, or the first harmonic, twice the plasma frequency. So here's the frequency they've observed the radio waves at. This is what's known as a dynamic spectrum. Here's time, and the color is the intensity of the radio waves. It's known as a dynamic spectra. Takes a little while. It kind of looks like the sun setting over the Pacific Ocean, but no, this is a dynamic spectrum. And radio solar physicists can look at these and really tell you a lot. This stripe here, they've given the unforgettable name of type 2 radio burst. This type here is a type 3 radio burst. You can see how long it takes to really get used to radio astronomy. But let me just tell you what they've learned. Type 2 radio bursts are produced from fast magnetosonic shocks. So this is what a solar physicist sees as a fast magnetosonic shock. And the frequency at a given time tells us the density that the fast magnetosonic shock is going through. This is actually the first harmonic, so this is the fundamental. Here, I've just done the exercise I'm sure you've all done of converting frequencies to electron densities. So this is 30 megahertz. This is an electron density of 10 to the 7 per cubic centimeter. 10 megahertz is 10 to the 6 per cubic centimeter. So the fast shock is going from high densities, up around 10 to the 8. That's sort of the density in the corona. And it's going out to lower densities, like 10 to the 6. This is the shock moving through the solar wind. Even more exciting, you'll notice, this is known as band splitting, that there's actually two type 2 radio bursts, one on top of the other. That's the first harmonic. The second harmonic, it's not so clear. Here you see it a little better. That tells us the pre-shock and post-shock densities. Right? It's a fast magnetosonic shock, so the density is increased. So the plasma frequency is increased. So we see two. You can't always see this in type 2 radio bursts. I've never gotten a radio astronomer to tell me exactly why. But here you have the density ratio, 1.59. So you can derive the Mach number. That is this Mach number. And actually where this shock here is at a given time, 325, well, this is 325 is way out here. 155, also way out there. You can see by the time you get to that density there, you're still very close to the sun. But this is how solar physicists see fast magnetosonic shocks in the radio. So actually we've done magnetospheric, we've done heliospheric, now we've done solar physics. The one thing we haven't talked about is the ionosphere. And Jan Soika has left the room. And I did this only for him because I thought we should mention the ionosphere at least once. And here's the interesting aspect of this. If you look at this spectrum, the reason this looks like the Pacific Ocean is we've cobbled together observations from 3 different radio telescopes. Learmonth, I believe, is in Australia. This, I don't even know this radio telescope. It's in an island. The eye is island. What? Bruny Island. There you go. Where's Bruny Island? Excellent. Okay. So Bruny Island, also Tasmania, as I understand it, is on Earth. Doesn't seem that way, but it is on Earth. This portion of the radio spectrum from SWAVES is from the stereo spacecraft. Okay? The reason we've had to go off Earth is because this dividing line here, 3 times 10 to the 6 electrons per cubic centimeter, is basically the density of the daytime ionosphere when there's been a flare. Of course, why would you be doing solar radio astronomy if there hadn't been a flare? So you have to deal with the ionosphere when it's at its densest. And the waves aren't going to propagate through the ionosphere if they're below that frequency. So everything above whatever 20, 30 megahertz you can do from beautiful places in Tasmania or Australia. Everything below that you have to do from space. Okay, so here's our exploration. These coronagraphs are made in space, and these radio observations are made in space because these radio waves don't get to the Earth. Okay, so that's the role that ionospheric physics plays in this. It basically costs us 100 times as much to get these radio observations as to get these radio observations. You got to go to space to do it. All right. Finally, a little breaking news. Last month, I showed you a picture of the bow shock. This is the, unfortunately, one thing IBEX seems to have discovered. IBEX is the interstellar boundary explorer. We heard about that on the first day. Is that the solar wind is flowing from the right of the diagram, not the left of the diagram as Steve Seuss had it. And it's flowing at about 23 kilometers per second. And I had shown you that that is higher than the sound speed. However, there is a magnetic field. And the IBEX has been actually exploring what the magnetic field strength is and what the magnetic field direction is. And what they have concluded is that while this is much higher than the sound speed is about 13 kilometers per second, if you look at the magnetic field strength and you look at the possible densities, that where we think we are in this diagram. And these are things IBEX doesn't measure directly, but other people have tried to estimate them. And they're pretty sure the density is higher than 0.07 per cubic centimeter, and that the magnetic field strength is somewhere north of 3 microgauss. In that case, the fast magnetosonic speed is 26.8 kilometers per second at this angle. One thing IBEX has done is found us the angle between the flow and the magnetic field direction. So we know that angle. The angle is 45 degrees. At 45 degrees, the fast magnetosonic speed, those of you who've studied this know that the speeds depend critically on directions, is 45 degrees. And this number is bigger than this number. So we are in a regime where the interstellar medium is not surprised by our solar system. It knows we're there. Fast magnetosonic waves move out in front of us and create not a shock. It's not a surprise. It's just a standard, we've got something up ahead. We better start merging right, getting off, and flowing around us in a nice smooth flow. So that's, as of May 10th, there is no longer a bow shock in front of the solar system, as far as we know. Okay, stay tuned. So exciting new development there. Just to give you an idea, if, for instance, we had a slightly smaller magnetic field strength, that's when people really thought there was a bow shock. So fast shocks. Fast shocks seems to be the thing that we're seeing all the time. Where do slow shocks come into all this? Probably the most famous place you're going to encounter slow shocks is in magnetic reconnection. Remember, in a slow shock, the post-shock material has a higher plasma pressure, a higher temperature, but a smaller magnetic field strength. And when Professor Bhattacharjee told us about how magnetic reconnection is supposed to work, it's going to reconnect magnetic field lines that are going one way and the other way, and in the region between them, the magnetic field will be weaker, and it will be hotter. So this was Petchek's revelation that there would be slow magnetosonic shocks that basically separated the pre-reconnected field from the post-reconnected field. And here's a two-dimensional simulation showing exactly that, where these slow magnetosonic shocks occur. Here they are in the context we expect them in, for instance, in the solar flare scenario. We have reconnection there. We have slow magnetosonic shocks that come out from the reconnection point. Here, the outflow hits the material below it and actually is slowed down. So the shock normal is pointing up here. The density is higher here. The magnetic field strength is also higher here. So in this case, we also have a fast magnetosonic shock. Here it is blown up. So the slow magnetosonic shock reduces the magnetic field strength. The fast magnetosonic shock increases it a little bit afterwards. And that occurs, they think, at the top of this. Have we seen these in reality? They are tricky. They're tricky to see. And I could go into details about why that is. But here is an observation from IC1. This is not at the bow shock. That's a fast shock. But at the magnetopause, which we think is a tangential discontinuity. The way reconnection really seems to work is a tangential discontinuity is a current sheet, and we can get reconnection at that current sheet. Essentially what the reconnection does then is causes the tangential discontinuity to break into a set of shocks, slow magnetosonic shocks. So when there's reconnection going on, instead of a tangential discontinuity or a rotational discontinuity, you actually will see a slow shock. And here's IC1 flying through such a thing. Here is the density. The density drops, so obviously this is pre-shock. This is the magnetosheath. This is the lobe, or the magnetosphere with the higher density. And as we go across in that same direction, where is magnitude of B? There it is. The magnetic field strength goes up as the density goes down. So it's a slow magnetosonic shock. So we do actually see them. They're not all that easy to see. Intermediate shocks now. Where do those come in? Turns out when Petchek did his model in 1964, he considered only the case of perfectly anti-parallel magnetic fields reconnecting. So you get slow shocks. if there were any angle other than 180 degrees between those magnetic field lines, that doesn't work that way. Actually, you get an intermediate shock, and here he is in 1967. So he came up with his model in 64. Everyone knows about that model. He had to revise it because Peter Sweet pointed out that it wouldn't work except in the extremely, statistically improbable situation of 180-degree reconnection, that the whole model didn't work. In 1967, he said, of course it does. There actually are two shocks. There's a slow shock and there's an intermediate shock. Okay? And so what happens is the intermediate shock changes the direction of the magnetic field mostly, not so much its magnitude, and the slow shock changes the magnitude. Here, in the same kinds of simulations I was showing you before, the magnetic field vector is to the right, to the left. They reconnect, but there's also a component coming out of the board. And in fact, you see time-dependent intermediate shock. You see slow shocks. You do, in fact, in simulations, see exactly this kind of thing. So intermediate shocks are important. Now, I want to get, in the couple of minutes I have left here, to return to this issue about entropy. Remember, entropy was essential. We cannot have a shock unless I can convert kinetic energy of the flow to thermal energy. Kinetic energy of the flow is all the particles, they're all moving coherently in one direction. Thermal energy, they're all moving randomly. So something has to randomize their velocities. If the density is high enough so we have lots of collisions, then that's viscosity, and that's what does it. In these plasmas that don't have high densities, like the solar wind, like the interstellar medium, like the magnetosphere, collisions aren't all that effective. So how do we see shocks? Well, that is the most exciting, interesting part of this story. So I've sort of given you the background so you understand what a shock is. You could spend the rest of your career trying to understand how thermalization occurs. And people have been doing this for a long time. There's many more ideas than there is consensus on the solution. But instabilities, chaotic particle motion, all sorts of plasma physics effects will actually randomize the motion. It's also going to help create non-thermal particles. So it thermalizes and non-thermalizes. Some of these random electric fields, instead of just creating a sort of statistical equilibrium between the particle motions, will create a few special particles that are going very fast. So when we see particle acceleration, very often it is thought to be related to shocks, and it is thought to be related to the thermalization processes related to shocks. It is easier. If the shock comes in, the particles are gyrating around the magnetic field lines, and that's somewhere close to the direction of their motion is perpendicular to the direction of the magnetic field. So perpendicular shocks. Shocks where the angle theta 1 is significantly larger than 0 means that you get this gyro motion to help in the thermalization. So perpendicular shocks occur much more frequently, or easier to observe, and have scale lengths that we can understand. Quasi-parallel shocks, I learned from trying to understand these, that people kind of decided that it was a problem a little harder than the other, and so they were drawn to the easier case. So you'll often hear people talking about whether the shock is quasi-parallel, quasi-perpendicular. The reason we really need to know that is it has a lot to do with how these particle motions occur and how this randomization might occur. All right, so just to summarize, I'll just leave up the figure here with all the different shocks that we think are occurring in the solar system, and ask here for groups to tell me, do you want to work on, I realize there's not a lot of time this evening, but maybe sometime you'll find some spare moments to look at either problem 1, thinking about the magnetopause and actually deriving the distance, the standoff distance between the magnetopause and the bow shock. Okay? So you could say if you know something about the magnetosphere, maybe that's something you want to do. That involves a little trigonometry and a little bit of trigonometry and working with a stream function of a flow. Problem 3 is much more just punch numbers into a calculator. It involves figuring out whether you've got a fast shock or a slow shock in measurements of the solar wind speed and magnetic field direction, and working out what the shock normal is. Sort of shows you that from these simple measurements, Bx, By, Bz, Vx, Vy, Vz, you can figure out all these properties, including the plasma beta. I'm not going to ask for the plasma beta, but the Mach number, things like this. So, which groups want to do problem 1, magnetosphere? So I see group, oh, they've ripped down the group numbers. No, you're group 7. Okay, I see group 7, magnetosphere. Now, don't worry if you don't know anything about, these are the 2 problems in areas I know nothing about. I know absolutely jack about the magnetosphere, and I know jack about the solar wind, but these problems are, you don't need to know anything, because I don't know anything. Problem 1, group 7. I want to see 3 other groups, come on. You're not in a group, but you could do it anyway. You're group 4. Group 4, group 7, group 3. I'm assuming, right? Group 3. Oh, you're part of 4. Group 3. I'm making group 3. And how about group 8 back there? Lucas. Okay. And then the other groups, 1, 2, 5, 6. Do problem 3. Work out the shock normal alphane Mach number in the solar wind, and then we'll go over that tomorrow. And so that is exactly 90 minutes. So thank you very much.